Hello, my wonderful calculus students. Today we're going to cover 1.8, which is infinite limits and limits at infinity. Okay, so there's two different types of these limits. We tend to get them confused because they both use the word infinite. So infinite limits occur when a limit as x approaches some constant variable. Okay, some constant value where a is a real number. Okay, and the result is either a negative infinity or a positive infinity in which it approaches. So for instance, let's look at x equaling 2. If we approach the limit as x approaches 2 from the left, you'll notice that it goes to negative infinity. And if you notice that as x approaches 2 from the right, it goes to positive infinity. So this is known as an infinite limit. Okay. The next one is called limits that go to infinity. This occurs when we have a limit as x approaches positive or negative infinity. And it results in having an end behavior that is either positive or negative infinity. Okay? So this could occur where we have like a slant asymptote, or it could occur when we have like a horizontal asymptote. But the key here is that the limit is where x is approaching either positive infinity or negative infinity. Okay, so you'll see these examples here. Like for instance, if we were to do what's the limit as x approaches -1 for g of x, you'll see that it's as x is approaching -1 for g of x, from the left it's going to negative infinity, and from the right it's going to positive infinity. Okay. And then same with the limits of infinity here. If we do as x approaches positive infinity, you'll see that the limit is going to infinity. And as x is approaching for g of x, okay, so for f of x, the limit as we go to positive infinity is going to 2. And if as x is approaching negative infinity, it's also going to 2. Okay? So just got to make sure you look at the right function that represents the graph. Okay. So now that we must develop an analytical procedure by which we can find limits at infinity. So for instance, we have this x is approaching infinity. If you plug infinity into all this, it's going to tell us that it's going to infinity. Okay, so this right here, since the degree is odd and the leading coefficient is less than 0, the graph will fall to the right. Okay, so think of these, this is a cubic function that's reflected over the x-axis. So when we look as x approaches to the right, the y value is decreasing. It's going down, and so this would be going to infinity. Okay, as x approaches negative infinity on this guy here, we look at the root here. This is going to be an even root because we have a square, we have a 1, and we have a 1. So this root is 4. It's an even function. And we know that it's going to be even, and the lead coefficient is greater than 0. Okay? Because this value here is going to be positive, and this value here is going to be positive. This value here is positive. So we say that this thing is an even function that's opened up, so the end behavior from negative infinity would be going to positive infinity. Okay, and then this next one is a rational function. We look here, we have we look for horizontal asymptotes. So horizontal asymptotes occur when we look at the numerator and the denominator are equal. So notice that the highest power in the numerator and the denominator are the same. We take the lead coefficient. In this case, that would be -2/1, which gives us -2. Something that we've done in pre-calc that we may have to go over again later. Okay, so here we have some examples of some functions here. Our third example, we have that 3 minus 2x over x plus 3 will provide us a basis for developing our analytical process. Okay, so for instance, we have this 3 over x. If you look at 3 over x and the limit as x approaches negative infinity, it's going to approach a y equals 0. Just like if we had as x approaches positive infinity, the limit is going to 0. Okay. And then this guy here, this 1 over x squared, you'll notice that as x is approaching negative infinity, it's going to 0. As x approaches positive infinity, it's going also to 0. But you'll notice that if we have x approaching 0, the y value from the left and the right is also infinity. Okay, so what does each of these functions have in common algebraically, and what do they have in common graphically? So algebraically, the numerator is a constant and the denominator is the same power in x. Okay, so notice that here the numerator is a constant for both of these, and the denominator is the same power of x. Okay, they have both vertical asymptote at x equaling 0 and the horizontal asymptote of y equals 0. Okay, there's that. Now, in pre-calculus, we learned 3 rules that determine the existence of horizontal asymptotes of rational functions. Okay, and those 3 were whether the horizontal asymptote is y equals 0, the horizontal asymptote is where the numerator and the denominator are the same power, giving us the Lie coefficient, or we have a slant asymptote. So these 3 examples are showing us how we find limits that go to infinity. Okay, limits that are at infinity. So what we do is we take the highest power in the denominator and we divide it to every single one of these terms, and we set the limit where x is approaching infinity. Or if it had negative infinity, we would do that too. And you're dividing each of these terms to find what the horizontal asymptote is. And so you'll notice that each of these times we're taking the highest power in the denominator and divide it to every single term in the rational function. And you'll notice that things will start canceling out and simplifying. And then at that point, we can plug in our infinity. Okay, so we can plug in infinity in here, 7 over infinity. Whenever we have a constant over infinity, we always say that it's 0. As our denominator gets larger and larger and larger, and it's being divided by a constant, it's going closer and closer to 0. So we say that a constant over infinity is always 0. So that's why we have this 7 over infinity turn into a 0. That's why the 6 over x squared turn into a 0, because a constant over infinity is 0. Okay. This last example, you'll notice that if you plug in infinity after you divide every single term by x, you're going to get x plus 3 plus 2 over x divided by 1 minus 1 over x, and then you're going to plug in your infinity in for x and solve. Infinity plus 3 is just infinity. So this tells us we have a slant asymptote on this last example. Okay, here's some more examples, but this time with negative infinity. All you're doing is you're just plugging in negative infinity into all of these, and they're going to obviously give you 0 each time there is a variable of x in the denominator. Okay, same thing with this. So if our x is approaching negative infinity, it does not make a difference if the graph is contained a horizontal asymptote. But as we approach negative infinity, it does make a difference if the graph contains a slant asymptote. So notice here, if you approach x approaches infinity, this went to a positive infinity. But as x approached negative infinity, it went to negative infinity on this one. So sometimes we have to do a sign chart for these. And we'll get to that in a moment here. So an example of this, we notice that the degree in the numerator and the denominator are the same. They're the highest power. We take the Lie coefficient, that would be negative 2 over 3. This guy here, we divide every single term by x, and we'll notice that this also approaches infinity. Now, we could also show this because the numerator has a higher exponent than in the denominator. We could do a thing known as long division to find, to simplify this, and then find infinity. So we can definitely do some of that practice in class. I'll show you in class. Okay. Here's an algebraic approach with a square root. So whenever you have a square root and you have an x squared inside, the square root of x squared is equal to x as long as x is greater than 0. Okay. The square root of x squared is equal to negative x if x is less than 0. Okay, so this is going to come in handy, especially if you have x approaching positive or negative infinity. So since this is approaching positive infinity, we're going to use the positive x because it's greater than 0. If it were negative infinity, you would use the one that's less than negative x, and you would divide it to each of your terms. And so that's how you would simplify this. And these are how we find horizontal and slant asymptotes using limits. Okay, I hope that was helpful. If you have any questions, please make sure you jot them down. Try to do the homework, look over some of these notes, and I would love to help you with this, the concept over infinite limits and limits at infinity. I hope you have a wonderful day, and I enjoy the calculus. We got many more lessons to go. Have a great day.